Thank you. So this is joint work with Lior Wolf from Tel Aviv University and Facebook AI Research. So what we're gonna do is first introduce the problem in the background, then show the model that we propose, which is explainable metatrees, talk about experiments we had with this model and some analysis of its behavior, and then suggest possible future work and extensions. So actually, Irad from the previous talk saved me a lot of work talking about explainable AI. So we all know that explainable AI is very important, and it's becoming more and more important as AI systems are becoming have more impact on users. And today, the common approach to explain machine learning model is to basically start by training a model and then focusing only on the performance of this model. And then after you have the trained model, you take some explanation method and try to explain your prediction. And as Irad said, there is like a family of such methods, which is local methods. These include Lime and Chap and Anchor and more, that they try to provide explanations for specific predictions of the model. And the general way that they work is that they sample the local environment of the current example. They look at what the model says about this sample, this new sample, and then using the model predictions, they try to provide some explanation in different ways. The problem is that these methods are many times disagree with the true logic of the model. So when you actually examine like real changes in the data and how the models react to them and what did the explanations say, then you see that there is disagreement. And actually, there are now papers that show how you can take a model and then wrap it somehow in order to fool these explanation methods, in order to hide biases that you might have in the model and you don't want anyone to be able to see. And the main reason why these methods are problematic is because first, it's a bit naive to use the representation that methods like Chap and Lime have for local environment that might be actually very complicated in terms of the logic that the model has for these environments. And second, when you sample near the current example, then you can generate new data points that are actually completely improbable to be in the data set. So these suddenly you show the model examples that it never saw before and is very different than what it did see in the training set. And therefore, the predictions that the model provides is you can't really trust on these predictions. What we try to do in this work is instead of training and then trying to explain, we try to build a model that is already self-explainable. And in the case of recommendation systems, providing explanation is very important because of different factors, but the main ones are that basically when you have a recommendation together with an explanation, it's just more convincing to the user and just converts better. And second, without an explanation, a user can think that maybe there is some discrimination that is happening, that there's like a reason that you don't want to show of why you recommended this item to the user. And by providing an explanation, you avoid this possible problem. What's going on in recommendation systems right now is that state-of-the-art models are usually implemented as deep neural networks, and deep neural networks are hard to explain. And they also have this, if you know a bit about recommendation systems, and they have this shared embedding space where both users and items can be mapped to this space, and then using some interactions within this space, you can improve the performance of these systems. The problem is that this space, again, is if you look at the values in this space, there again, you cannot really understand the meaning of it. And then when most explanation methods in recommendation systems, what they do is they use this embedding space, and they apply usually some distance metric. And then they can find, for example, items that are similar to the current item or users that are similar to the current user. And then they can tell you things like, so you rated this item and highly, and this is why we recommend you this item. But to say that this is exactly explains the logic of the model is not exactly correct. One model that is very explainable is decision tree. And decision tree, if you look at the decision tree, then you can understand the whole logic of the model. And also, if you try to explain a specific prediction, then you can just see the path that the current example took from the root to the leaf node, and you can understand exactly why did we get the prediction. So then, what we would like to do is we would like to apply decision trees for recommendation systems. So there are two like naive ways, you can say, to try and do something like that. So the first one is to take the whole data set and then train one huge tree on this data set for all users and all items and hope that this thing will work out. The problem is that this is a bit too simplistic, and the performance when you do this is actually pretty bad. And you will see it in like later slides. This approach is what we call here global tree. So it's one tree that works for all users. And then another approach you can try is to use a decision tree for each and every user in the data set. So each user will be modeled basically by a decision tree. And then different users have different decision trees. And then the problem here is that by doing so, you cannot really share information between different users, so users cannot learn from each other. And because in recommendation data sets, usually you have many users with very few examples, so then what happens in reality is that you overfit for each and every user. So because you don't have many examples for each user, you train a decision tree. The decision tree tends to just overfit if you allow it to be strong enough in terms of like how deep can it get. And then the performance is again poor when you evaluate on the test set. And this is what we call local trees in this presentation. The last part of the background is what's called few-shot learning. So few-shot learning is a paradigm of learning that is under the family of meta-learning, or learning how to learn. And the idea in the setup in few-shot learning is that you have many tasks. Each of them is pretty small, and they are different, but they are very similar to each other. And then the idea is that instead of starting to learn from scratch every time you get a new task, you try to somehow leverage the experience you had from solving different tasks in order to now solve the new task efficiently in terms of the amount of data you need to get to good performance. So in meta decision trees, what we try to do is to learn such trees for every user, just like we saw in these local trees. But this time we're going to use few-shot learning in order to tackle this overfitting problem when starting from scratch to learn decision trees. Okay, so the first thing we'll do is we'll talk about the representation of meta decision trees. So few notations. So in recommendation systems, we usually have items. So in this case, we have items that are represented as X, and they belong to some space of dimension D. And then we have the ratings that were provided, which are marked as Y, and there are some positive numbers. And then if we want to represent a user, then we can represent a user by the pairs of items that the user basically rated. So we have the features of the item and then the rating itself. And then every user rated like a different set of items and provided different ratings for these items. So in this case, we have a user with n different ratings. And then if we want to understand how a decision tree look like, in our case, is a bit different than normal decision trees that we're used to. Then in meta decision trees, we have again inner nodes and leaf nodes, just like normal decision trees. But in this case, inner nodes can actually be represented by 3 different parameters. The parameters are W, B, and beta. And W is basically a distribution over the features in X. And then B is a bias term, and beta is a confidence term. And when we want to understand, to calculate the probability that a current example should go to the right child of an inner node, then we take the dot product of W and X, we subtract the bias, we multiply everything by beta, and eventually we take the sigmoid over this whole term. So what happens here is that W is basically some kind of a feature extractor from X, so it chooses what features should be used from X. We subtract some bias, and then we multiply by beta. So if beta is very close to 0, it means that this whole term will go pretty much to 0, and then the sigmoid will output a probability that is like 1/2. So if beta has a very low absolute value, then the sigmoid will basically say, I'm not sure. And then if the absolute value of beta is very high, then the sigmoid will shoot, depending on the sign of this term, then the sigmoid will either shoot 1 or 0 probabilities. So high absolute value of beta means that we are very confident in the rule that was chosen here by W and B. And then leaf nodes are represented as single values, just like in normal decision trees. So if you want to make now a prediction using meta trees, so let's say we have a tree T that has different inner nodes and leaf nodes, and we want to make a prediction for an example X, then we mark as T of X and Z to be the probability that example X reached leaf node Z. And this probability is basically to take the product of, so if we go from the root of the tree to some leaf node, then we have to pass through some inner nodes. We take all the probabilities that the inner nodes provided for this example, then we take the product of that. That's a probability that we get to the leaf node. And then we mark as VZ to be the value in the leaf node. So then when we want to make a prediction, we basically have some distribution over all leaf nodes. And then we take the weighted average of the values in each leaf node and the probability that the leaf node got. Okay? Okay, so now how do we actually learn like these trees, and how do we make them to be able to share information between different users so that we don't start from scratch? So the model basically contains 3 different functions. All of them are implemented as neural networks. What we do is we get a training set, again, pairs of X and Ys. And we have a mapping function H that can take such pair and map it to some vector in whatever space we define. Like we can define what space should this thing be. And then we do this mapping of H to each and every pair in the training set. And eventually we take the mean, we do mean pooling of these sets of vectors in order to get one vector which represent the training set. Now, if we want to create an inner node, we can apply F. F gets as input this representation of the training set, and F outputs the parameters that define an inner node, which are W, B, and beta. And if we want to create a leaf node, then we apply G, and G provides a single value that defines a leaf node. So then, using these 3 networks, we can actually create a single node of a tree. And now what we would like to do is to create a full tree. So what we do is we start with some training set of, let's say in this case, 10 examples, and we create an inner node. And this is done using this process. So we take the mapping of H and then apply F. And then using this logic that was found here, we can route examples either to the left or to the right. So now if we look, for example, at what happened in the left and we want to continue growing the tree, then we have a new training set now. We can map again this training set to some representation and get other parameters that define a different decision rule. So because we have a different training set in the root of the tree and in the left child of the tree, then we might get different rules in the decision tree. And then finally, we route again examples, let's say, to this leaf node, and we decide somehow that we want to stop growing the tree now. And this time we take these 2 examples. Again, we pass it through H, and this time we send it to G in order to get the final value in the leaf node. So by doing so, we can basically create full trees. And we have one mechanism, which are these 3 functions, that they create all trees. Okay, so how do we get loss on the whole thing? So what we do is we take all users in the dataset, and for each user we have the information, all the examples we have for it. We divide the examples to a training set and a test set. And then what we do is for each and every user, we take the training set of the user. Using the training set of the user, we create the tree in the process that we just described. And then for every example in the test set, we make a prediction using the tree, which is again the weighted average of the probabilities of the leaf nodes times the values in the leaf nodes. And then we calculate error, and in this case, we take the mean squared error as the loss. So what happens basically is that we have a training set. We have 3 networks. They are called recursively in order to create a tree. Then we take this tree, and we actually forget about these 3 networks. We take new examples, we pass them through the tree, we get a prediction, and we can calculate the error. Then this error we can propagate back through the tree, and then from the tree you can propagate it back to F, G, and H. And then F, G, and H can be updated by this process. So we have a network that generates a tree, and then this tree is used for prediction, but we can actually do training and learning for these 3 networks. In addition, we'd like to have nodes that are more explainable. So what we do is we have an additional loss term, which controls the sparsity of W. So if you think of vanilla decision trees, then in vanilla decision trees, we don't have really distribution on the features. We have actually only one feature that is being used. So you can think of it that W is not a distribution, it's just like a one-hot vector. So what we would like to do here is to push W towards the representation of one hot. The way we decided to do it is we take W and we do the cross product of W by itself. So then you have some kind of a matrix. And then if W has 2 different features which have non-zero probabilities, then we will have non-zero values on the off diagonal of this W cross W. So if we have, so again, if we have 2 features that have non-zero probabilities, then in the off diagonal of W cross product W, we'll have some positive numbers. So what we do is we take this matrix, we subtract the diagonal, and we try to minimize the L1 norm of this whole matrix. So basically, we push it towards having only zeros in the off-diagonal cells, and by that we push it towards one hot representation. So finally, the loss of this whole system is the loss on the prediction of these trees, and then the sparsity loss, and we introduce some hyperparameter lambda, which controls the sparsity of W's. Then we have different flavors that we can think of. So you can think of when should you stop growing the tree. So in vanilla decision trees we have information gain or gene reduction. In this case you can think of different methods on how to do it. We didn't really think of anything too fancy. So in our case we either used what's called fixed, where we decide on a maximum depth, and then we have a full tree for this depth, or we have what's called dynamic, where once we have an inner node that sends all examples to one side, then we stop. In addition, we also consider, instead of sending an example with some probability to the left and to the right, we consider just sending it to only one side, which actually really decreases the performance of these trees, but really improves the explainability. And we also consider transforming W just strictly to one-hot vectors, which actually doesn't really causes any loss in performance. Okay, so now we reach to the experiments. So we start with a synthetic experiment. In this synthetic experiment, the problem is a binary classification problem. So actually, I only talked about regression, but it's really easy to adapt the model to classification. You just, instead of using real values, G would output probabilities for the leaf nodes. And then instead of using mean squared error, we use the cross entropy loss. And that's basically the trees are ready to function now for classification. So what we did in the synthetic experiment is we have different training sets, just like we have different users in the recommendation systems. And then each training set is composed by vectors of size 10. And then if we want to determine what is the label for these vectors in this training set, then we choose 3 features. And there are some features that are more likely to be chosen than others. And then using some constant logic that can be fully represented by a decision tree, we determine what is the label. So basically, there is some overall prior on what will be the logic for mapping from X to Y, and which is not uniform. And we hope that F, G, and H can be able to encode this information in order to solve the task better than global tree, which is basically trained on the union of all these training sets, or local trees, which is starting to learn a decision tree from scratch every time it gets a new training set. So here you can see the performance of global tree, local trees, and both meta trees with respect to the size of these training sets. So you can see that global tree, because it just uses the union of this training set, doesn't really care about the size of each one of them. So it's pretty constant in performance. This is just noise. It should be like a straight line. And then you can see that local trees, they are becoming better and better as you have more and more examples. So they are able to figure out like what features should be used. And then meta trees, they start much higher, even though there aren't that many examples in the each training set, because they are able to understand what features should they go for if they don't have that much information, because there are features that are more likely to affect the label than others. Then you can see that when the training set is pretty small, then this gap is pretty large. If you take the training set to be very, very large, then eventually all these 3 models converge to perfect performance. The next thing we did is we actually used real recommendation data sets. So we have 3 different public recommendation data sets. 2 of them are for movies. They're called movie lengths 100K and 1 million. They're called like that because the 100K has 100K examples, and the 1 million has 1 million examples. And then we have gesture, which is another recommendation system for recommendation data set for jokes. So here you can see a comparison of meta trees. And then you have the 3 data sets. We have the root mean squared error and the mean absolute error. And they are compared to different tree baselines, and then like classic collaborative filtering baselines, and more state-of-the-art models. So you can see that meta trees basically outperform all 3 models which have the same level of explainability. I mean, these 3 models have the same level of explainability as meta trees, this one a bit less, and you go down in explainability as you go down in the table. And then you can see that MetaTrees is pretty competitive with SVD and SVD++, so they're actually behind for movie lengths, the 2 movie length data sets, and are ahead in gesture. And then you have the state-of-the-art models, which are actually outperforming our model. What was very nice when working on these data sets and using these MetaTrees is that when you introduce a new feature, you can look at the trees and you can actually see pretty easily what is the feature importance, for example. Because you just look at the trees that come out and you analyze them and you say, okay, this is how the model used this new feature I introduced. And you can understand the behavior of these trees and learn about the data. And this was something that actually for me was like, I didn't get to do it for a long time. So it was pretty nice. And now what we'll do is we'll talk about like an analysis we did over these trees that come out from the model. So when we looked at the trees that come out, we saw that there are generally 3 different types of trees. So the first one is exactly like the trees you would imagine. So you have some user, and like the user has some preferences, and they care, for example, they like better like action movies, let's say, or they like movies that came out in the 80s. So you see these features in the tree. But then there are also other trees. One of them is a basic collaborative filtering tree. So basically what it does is it takes the average rating of the item and just does rules only on this feature. So basically takes the average rating of the item and splits items to different bins according to their average rating. And then we have different leaves for each one of these bins. And if the user is very generous in his rating, then the values on these leaf nodes will be pretty high. And if it's not that generous, then the values on these leaf nodes will be pretty low. So basically adjusting the different bins to the scale of the user. And then we also saw that there are reverse trees, where basically we have exactly the same binning process of these average ratings, but the order of values in the leaf nodes are actually upside down. So these users basically, they just prefer bad movies or jokes. And this is something that having a black box system, you would never be able to find out that something like that exists in your data. And we saw that these trees exist for the 3 different data sets. And when looking at the data of these users, we saw that this is really what happens. Like, there is negative correlation between these 2 features. And in collaborative filtering algorithms, usually the way it works is that you actually normalize these effects. So you don't really take it into consideration. You don't allow even the model to learn that. Another thing we saw that was that we were pretty encouraged by is that these 2 type of trees that are eventually pretty simplistic, they work only on one feature, they were much more common for users that have very few examples. So basically, when the user doesn't have a lot of example, we saw that this mechanism is more like prudent about what features should be chosen to the tree. But when we have a lot of examples and we can already count that, okay, this user definitely doesn't like action movies, for example, then suddenly action movies will appear in the tree. So here you can see some examples of these trees. So first you see what comes out when you train just one big tree on the whole data set. So it only uses the average rating in the inner nodes. I'm not sure you can see it. And then you can see what comes out from our meta tree algorithm. So here you can see like one user where different like features were used, like whether it's adventure movie or what is the release date and the average ratings. And then here you can see these like classic collaborative filtering trees where you just use the average rating in order to bin it to different bins and then provide different values. And then here you can see that is not a full tree. These are the dynamic trees. Here it was like cutted. And again, uses different ratings. And this is actually a reverse tree that is very sparse. It was created also by the dynamic architecture. So finally, about possible future work and extensions. So what we thought that would be interesting to do is to use more sophisticated like stopping criteria and maybe do some tree pruning to these trees. Also applying these trees on other domains like finance or medicine, where explainability is very important. And then like more adventurous ideas are to, instead of creating a decision tree per set, maybe we can create a decision tree for every example. So we'll have like a decision tree that is created for an example. It doesn't really move much when the example changes a bit, but when you go to a completely different region of the data, then the decision tree can change like significantly. So it's kind of like local learning of decision trees. And then another thing one can think of is to, instead of using decision trees, which have like pretty limited representation, maybe you can think of another representation that is also very explainable, that you can enforce the model to pass through, and then you get this high explainability without damaging performance that much. That's it. If you have any questions.
A major advantage of the state-of-the-art collaborated filtering is that it uses uh, unlabeled data, just takes the preferences of different users and the movies, etc. And in your trees, we see that it uses um, named features like adventure, non-adventure, etc. So is the work using these trees with unfeatured data, as it were?
Yeah, so we did, it's a good question, and we did different like attempts. The problem is that it's hard to create explainable features when doing so, and then this is like another problem that you need to encounter. There are many situations where actually you cannot really apply this type of learning for recommendation systems. So think of it, for example, when you have a news website, for example, so news are becoming irrelevant after like one day. So you don't really have information about the usage of different users for this item, so you cannot really represent it using this collaborative filtering way. And then this is when things like that can become even more relevant. But yeah, you completely like.
Okay, we have to move further, so let's thank the speaker. Thank you.